Hi everyone, my name is Matt Ford and I'm an assistant teaching professor in the mechanical engineering program here at UW Tacoma. And this project was a collaboration with my colleagues Soheil Fatehiboroujeni, who's now a professor at Colorado State University, and Elizabeth Fisher and Hadas Ritz, professor and senior lecturer respectively at the College of Engineering at Cornell. In 2020, we transformed our materials testing labs in mechanical engineering, both to accommodate remote instruction, but also to give students a better opportunity to exercise decision-making and agency in their projects. ABET, which is the accreditation body for engineering programs, requires that we assess our students on their ability to develop and conduct appropriate experimentation, analyze and interpret data, and use engineering judgment to draw conclusions. I like to boil this outcome down to one simple sentence, which is that we want students to be able to make decisions that matter. Activities that we design should give students opportunities to practice making technical choices, and those choices should have meaningful impacts on the outcome of the activity. But if you look at how materials testing labs are traditionally done, they're typically done by following ASTM standards. ASTM standards are very detailed recipes for performing experiments, and they're an important tool for engineers to make sure that there's agreements on what constitutes a valid test. But they specify everything from the design of the specimen to the way that the experiment is done to how the data is analyzed. There's very little room for students to get practice actually making experimental decisions. Of course, there are a lot of ways to make an activity more open-ended. On one hand, you could just completely remove all of the constraints in the activity and give students complete freedom. On the other hand, you could impose new constraints by removing the tools that are typically used to solve the problem, and that forces students to be more creative in coming up with solutions. So we took this latter approach, and we asked the students to measure the stiffness of the material in an aluminum can with the restriction that due to COVID, they weren't able to use the sophisticated equipment available in lab. When talking about outcomes, I like to distinguish between what I would call genuine open-endedness in an activity and superficial open-endedness. So on the slide here on the left, I'm showing an image of a branching river delta. And although the river branches into many paths that take different routes, they all eventually lead to the same destination. Whereas on the right-hand side, I'm showing an image of an open field with a foot-worn path through the middle. The open field seems like it provides unlimited paths and options for people to walk, but because of the boundary conditions that are imposed by people's desires, where they want to go, their habits, everyone ends up following the same path. So the way that a seemingly open-ended activity is designed can effectively force students down the same path. If you hand students a standardized specimen, you send them to a lab with specific equipment but no instructions, they're all going to try to end up doing the same kind of experiment. But on the other hand, if you send them to an empty lab with no guidance or tools whatsoever, they'll quickly become frustrated. And it's important to strike that balance between guidance and open-endedness. And I think we struck that balance really well. And that's evidenced by the wide diversity of successful solutions that students were able to generate. I'm showing here on my screen a matrix where each column is a specific decision that students had to make in solving the problem. And the rows are different ways that they could make that decision or choices. And there are several dozen unique paths through this matrix, each of which represents a possible unique solution to the problem. So as an example, this red path that I'm showing on my screen here represents a group of students that chose to make a dynamic measurement on a cantilever beam with no applied load. They used a video camera to make the measurement, and they didn't do any additional amplification of the signal. We also found that the wide diversity of solutions was not just a product of many permutations of a small number of choices, but that students were really finding many successful solutions to each subproblem. I think this idea is so compelling that I also did it with my students here at UW Tacoma in winter 2022, even though the students were learning fully in person and we had access to lab equipment. So I have lots more exciting details to share, and I hope to chat and interact with you all in the synchronous session. Take care.